Okay, in the previous video, we saw that we had this relation for the AK sequence, AK plus 2 times AK plus 1 times AK plus 2 plus AK is equal to 0. And so now what we can do is we can solve for AK plus 2. And explicitly we get AK plus 2 is equal to minus 1 divided by K plus 2 times K plus 1 times AK. So AK plus 2 is defined in terms of AK. So what this means is that in general, the terms of the sequence are defined in terms of the preceding terms of the sequence. Okay, so for this particular problem, let's note the following. So assume we know A0 and A1. Okay, these are going to correspond to the arbitrary constants that you get when you find the general solution to a differential equation. But for now, let's assume that we sort of know what they are in the sense that they're arbitrary constants. Okay, then we can compute A2. Okay, we want to use this formula to compute A2. In this case, K is equal to 0. And so A2 is equal to minus 1 over 0 plus 2 times 0 plus 1 times A0, or this is minus 1 over 2 times A0. So A2 is equal to minus 1/2 times A0. Okay, A4, okay, if I want to compute A4, that means K is equal to 2 because 4 is equal to 2 plus 2, and again, I want to use this formula. A4 is equal to minus 1 over 2 plus 2 times 2 plus 1 times A2. But what is A2 equal to? Well, I'll have the first part, minus 1, 2 plus 2, 2 plus 1 times A2, which is just minus 1/2 A0. And altogether, this is going to be 1 divided by what's going on in the denominator. This is 3, this is 2, oh sorry, this is 4, this is 3, this is 2, and so in the denominator we have 4 times 3 times 2, otherwise known as 4 factorial times A naught. And we can continue this pattern, and for this particular case, the even coefficients are only defined in the preceding, defined in terms of the preceding even coefficient, and similarly the odd coefficients are going to be defined in terms of the preceding odd coefficients. Okay, and so that's going to dictate the next choice that we make when we try to determine a general formula for the AK, which is what we're going to do now. So now we want to determine a formula for the AK sequence, and we're going to break it up into two cases. One case is going to be when K is even, and the other case is going to be when K is odd. Okay, and AK plus 2, given this formula, is equal to minus 1 over K plus 2 times K plus 1 times AK. Okay, but now I want to write out what AK is, again, using this formula. So I'll just have the minus 1 over K plus 2 times K plus 1 times AK, and again I'm going to use this formula, but now the index is K instead of K plus 2, and so the formula is minus 1 divided by K times K minus 1 times AK minus 2. And now if I wanted, I could write AK minus 2 in terms of AK minus 4. So what's going to happen if I continue this pattern down all the way, I can continue this pattern all the way down until K minus 2 is equal to 0. Okay, and I'm going to have a factor like minus 1 over K plus 2 times K plus 1 times the next factor minus 1 over K times K minus 1. And this is going to go all the way down, and the last factor is going to have something times A0. Let's figure out what that something is. Well, if K minus 2 is equal to 0, this means that K is equal to 2 and K minus 1 is equal to 1. Okay, so if 0 is equal to K minus 2, this means K is equal to 2, and so this last factor is going to be minus 1 over 2 times 1. Okay, and so now let's try to figure out what's going to be in this kind of missing, these missing factors here. Well, notice what's happening. So I have a k plus 2 times k plus 1 times k minus 1. In the next factor, it would be a k minus 2 times k minus 3, all the way down to 2 times 1. So in the denominator here, I'm going to have k plus 2 factorial times a0. Okay, now I have these minus 1s in the numerator. So if there is an even number of factors there, that's going to be like minus 1 raised to an even power. If there's an odd number of factors, it's going to be minus 1 raised to an odd power. What that tells us is that we're going to have something here in the exponent that's going to alternate making the minus 1 to a power, either a positive number or a negative number, based on whether or not there are an even or odd number of factors there. And we're going to leave that blank for now, and we'll figure it out in just a moment. There's a couple of reindexing things that we need to do. So the first reindexing thing is that notice that this is explicitly a formula for k plus 2, but really we can write this as a formula for ak. And so again, when k is even, the formula is minus 1 to the power of something that we'll have to figure out times k factorial times a0. Okay, the next sort of more major reindexing thing that we want to do is the following. If k is even, this means that k is equal to 2n for some n equals 0, 1, 2, so on and so forth. So I'm going to make that substitution now. So a2n is going to be equal to minus 1 to something divided by 2n factorial times a0. Okay, and so now if we come up here, if we come back up here, we want to determine whether or not there are an even or odd number of factors. Okay, so if we come down here, if n is odd, there's going to be an odd number of factors, and if n is even, there's going to be an even number of factors. Okay, and so what this indicates to us is that in the exponent here, we want to put an n. And just to make sure of things, we can do the following check. So if we use this formula when n is equal to 0, this will give us a formula for a0. Okay, and if we use the right-hand side of the formula, this is minus 1 to the power of 0 divided by 2n factorial a0. Minus 1 to the power of 0 is 1. 2n factorial, well, if n is equal to 0, that's 1. And so this is just equal to a naught. But of course, this is equal to a naught. Okay, so by choosing an n there instead of an n plus 1, it tells us that, that's the right choice. This indicates, this little computation here indicates that we picked the right choice. Okay, and so this is the formula for ak, or a2n for even k's. And I'm not going to go through the whole procedure, I'll let you do that. But if k is odd, then we can write it as 2n plus 1. And a very similar argument shows that this is the formula. Okay, so this is good. We have a formula for the AK sequences when k is even. That would be this one, and a formula for the AK sequence when k is odd. That would be this one. And so now what we're going to do is we're going to plug these into our sequence, or our series, our power series, AK t to the power of k. The first thing we're going to do is we're going to split this into an even sum and an odd sum. So we'll index this n equals 0 to positive infinity, a2n t to the power of 2n. You should remember doing similar things in Calc 2. N equals 0 to positive infinity, a2n plus 1 t to the 2n plus 1. And now we're just going to plug in our expressions for these coefficients. So this is going to be the sum, n equals 0 to positive infinity. Okay, what is a2n? This is minus 1 to the power of n divided by 2n factorial a0 t to the 2n plus the sum n equals 0 to positive infinity. a2n plus 1 is minus 1 to the power of n over 2n plus 1 factorial a1 t to the power of 2n plus 1. Okay, but notice that a0 and a1, these are just constants as far as the summation variable is concerned. So I can rewrite it like this. Okay, so I'm going to call these two functions. So this series, I'm going to call x1 of t, and this series, I'm going to call x2 of t. And I'm going to make some observations. So notice that this whole expression here is a solution to the differential equation for any value of a0 and a1. So if a0 is equal to 1 and a1 is equal to 0, we can conclude that x1 of t is a solution. Okay, similarly, if a0 is equal to 0 and a1 is equal to 1, we can conclude that x2 of t is a solution. Okay, so x1 of t and x2 of t are solutions to the differential equation. They're going to form a fundamental set of solutions if they're linearly independent. And how can we determine whether they're linearly independent? Well, one way is by using the Wronskian. So remember, there's this fact that says that if the Wronskian of two functions is not equal to 0 at some point, so if we can find some point where this is not equal to 0, it means that the two functions are linearly independent. Okay, so we're going to compute the Wronskian when t is equal to 0. So we need to compute x1 of 0. Okay, so if I come back up here to my formula for x1 of 0, if I plug in t is equal to 0, well, what's going to happen? Well, when n is equal to 0, this is going to be 0 to the power of 0, which is 1, minus 1 to the power of 0 is 1, 2n factorial, if n is equal to 0, is also 1. So this tells me x1 of 0 is equal to 1. Now for x prime of 0, I need to compute x1 prime of t. Okay, so x1 prime of t is going to be the sum n equals 0 to positive infinity minus 1 to the power of n over 2n factorial n times, 2n times t to the power of 2n minus 1. Okay, so now observe what's going to happen. Well, when n is equal to 0, this term is equal to 0 because that n is equal to 0. So we can start the summation when n is equal to 1. Okay, but now what's going on, if I plug in t is equal to 0, well, 2n minus 1, that's always going to be greater than 0 if n is bigger than 1. So if n is equal to 1, 2n minus 1 is equal to 1. And so if t is equal to 0, and 2n minus 1 is bigger than 0, it means that's always going to be equal to 0. So in other words, this implies that x1 prime of 0 is equal to 0. Okay, if I plug in t is equal to 0, this series is 0. And similar computations will show you that x2 of 0 is equal to 0, and x2 prime of 0 is equal to 1. So the Wronskian of x1 and x2, if you don't remember, this is x1 of t times x2 prime of t minus x1 prime of t x2 of t. And so for our functions, if we evaluate these Wronskians at 0, or this Wronskian at 0, we get x1 of 0 times x2 prime of 0 minus x1 prime of 0, x2 of 0, and this is 1 times 1 minus 0 times 0, which is equal to 1, which is of course not equal to 0. So what this shows us is that x1 and x2 are linearly independent. This argument up here shows that x1 and x2 are solutions to the differential equation. So it means that x1 and x2 form a fundamental set of solutions. In other words, any solution to the differential equation that we're considering can be written as a linear combination of x1 and x2. And the coefficients a0 and a1 correspond to the arbitrary coefficients that you get when you solve a second order differential equation. We know the solution to the differential equation is given by c1 cosine of t plus c2 sine of t. We're just doing this as an example to illustrate the method, but also observe something that works out very nicely is that this is the series for cosine and this is a series for sine. In other words, x1 of t is cosine in this case, and x2 of t is sine of t in this case. Okay, so this is kind of a complicated way for solving an easy problem, but where this method is really powerful is when we're solving equations that do not have constant coefficients.